Okay, so let's get started. So let's start with a summary of last time. Last time we introduced what was called the Legendre transformation. And it allowed us to describe a system using two different functions. So allowed us to describe a system using, on the one hand, the Lagrangian, which is a function of the generalized coordinates, the generalized velocities, and time. And so if you recall, when you solve a problem with the Lagrangian, you would write that L equals T minus V. Then you would use the Euler-Lagrange equation, and then you get second order ODEs for the functions, the generalized coordinates as a function of time. And the second option we found, so using the Legendre transform, that we could define this new function h to be the Legendre transform given by the sum of I equals 1 to n of pi qi dot minus L. And that thing was called the Hamiltonian. And then today we'll see how we solve a physics problem using the Hamiltonian. So to go back and forth, so this Hamiltonian, we also showed that it can be written as a function of the Qi, the Pi, and the T, where Pi are the generalized momenta, in particular, we spent a lot of time showing that H doesn't depend on the Qi dots, and that it's possible to write H as only depending on the Qi's and Pi's. So we've truly performed a change of variables where we've replaced the Qi dots by the Pi. And we've promoted the Pi to be proper variables that describe the system on the same footing as the coordinates. And to go back and forth, so we have the definition of H, that's the transform that allows you to calculate to go between H and L, and then to remove the coordinates, we found these transformation equations. So the PI's are given by the di L by di Qi dot. So if you want to go from L to H, you have to define the PI's as such. If you're going the other way around, we found that the Qi dots are given by di H by di Pi. we found that di H by di Qi is equal to minus di L by di Qi. And a very similar equation was that di H by di T is minus di L by di T. So remember here, the QIs are variables that we keep in both H and L. And then the PIs, or the QI dots, are what we called the active variables. In the Legendre transformation. So they're the ones that we get rid of. So the QI, we call those passive. Okay, so any questions about that? Okay, so now let's go to what are called the canonical equations. Well, I'm wondering, is today a holiday or something like that? Is that why nobody's on? Tomorrow's a holiday. Yeah, I would have thought Remembrance Day was November 11th, right? So, like, there's classes and everything going on at USD today, right? Okay. All right. I just thought that was weird. Okay. So let's keep going. So the canonical equations, they are like the Euler-Lagrange equation when you're doing Lagrangian mechanics, right? So they're similar to the Euler-Lagrange equations in the Lagrangian formalism. So i.e., they give the equations of motion. So recall the transformation equations if you're going back and forth between H and L. And so there's a mistake in the notes here. So I've updated the notes and you should re-download them. Let me put a sign here since most people are missing this. Also, the notes that were online are missing a section. So I'll just put a note here since a lot of people are missing this lecture. Hopefully they read the handwritten notes. All right. So the transformation equations, we had that Qi dot is given by di h by di pi, right? And then we had that pi is equal to di L by di Qi dot. Right. So this are the transformation equations. For the Legendre transform. So recall the Euler-Lagrange equation. The Euler-Lagrange equation is d by dt of di L by di Qi dot minus di L by di Qi equals 0. So di L by di Qi dot, of course, is pi. And so what this tells us is that d by dt of pi is equal to di L by di Qi. Now recall, for the passive variables, we had di L by di Qi was equal to minus di h by di Qi. So if we combine all of this together, so d by dt of pi is pi dot, right? So we find that pi dot is equal to minus di h by di Qi. So if I take this equation and the other equation that I had here above, the Qi dot one, we can write out what are called Hamilton's canonical equations. And those are that Qi dot is equal to di h by di pi, and pi dot is equal to minus di h by di Qi. So these are the equations of motion in the Hamiltonian formalism. Okay, so they're pretty because they're first order derivatives in time, and the time derivatives are separated from the space derivatives. So you have d by dt of something on the left-hand side equals some other function. So this gives us 2n first order ODEs with the d by dt's separated out. So that was really the key contribution from Hamilton, was to be able to figure out that this alternative description gives you equations of motion that are mathematically considerably simplified. So these are called Hamilton's canonical equations. you'll notice that if a coordinate is cyclic in the Hamiltonian, the conservation of the associated generalized momentum is automatically is trivial, right? If Qi is cyclic in the Hamiltonian, by that I mean that dih by dqi equals 0, then pi is equal to a constant. That's the second canonical equation, right? If pi dot is equal to 0, then pi is a constant. So the conservation of the associated momentum falls out immediately from its conjugate coordinate being cyclic. Now, when you have a real problem, when you try to solve it, you might end up with the second order equation when you carry out the math and you plug in pi dot back into qi dot. But we'll see examples of that. And it all depends on whether, when you're trying to solve a system, maybe you're only interested in how position and momentum vary. And so then you have the equations right away. But it's possible that when you try to solve for the position as a function of time, that you have to put in the equation for the pi dot and end up with the second order ODE. But those are things we not so concerned about. So consider now, so let's look a little bit more at this function h, this Hamiltonian. So consider the time derivative of h. So we want to calculate dh by dt. So we're just going to apply the chain rule. So remember, h is a function of qi, pi, and t. Right? So dh by dt is sum from I equals 1 to n of dih by dpi, pi dot, plus dih by dqi, qi dot, and then outside of the sum, plus dih by dt. Now let me sub in the canonical equations into this. So you notice that this part here is qi dot, and this part here is minus pi dot. Just substituting in the two canonical equations that are boxed. So that means that we really have, this is equal to the sum from I equals 1 to n of qi dot, pi dot minus pi dot, qi dot. Of course, that's 0, plus dih by dt. And so then we find that the total time derivative of the Hamiltonian is equal to its partial derivative, regardless of its form, right? And I compare with that with the fact that dl by dt is not equal to dl by dt. The total time derivative of L with respect to time is not the partial derivative. They're not equal to each other. And the main reason is because L depends on Qi and its time derivatives. So there's no way they're going to cancel. But here we've proven that the total time derivative of H is identically equal to its partial time derivative. So also recall that di H by di T is equal to minus di L by di T, right? That was one of the properties of the transformation. So what that means, if di L by di T equals to 0, then di H by di T obviously also equals to 0. And of course, di H by di T is equal to dH by dt. So if di L by di T equals 0, then H is equal to a constant. So of course, H has the same form as the Jacobi integral. And that was given by the sum from I equals 1 to n of di L by di Qi dot times, what was it equal? Qi dot minus L. And if di L by di T equals to 0, and the potential di V by di Qi dot equals to 0. So we found that if the Lagrangian didn't depend explicitly on time, then little h was conserved. And furthermore, if the potential didn't depend on the velocities, we found that h was equal to t plus v. Which was E, the total energy. So similarly, if V is not a function of the velocities, then this thing we call the Hamiltonian H is equal to the total energy. So the Hamiltonian we can write as T plus V. But that's only a shortcut, right? So if the potential doesn't depend on velocities, then you can write this Hamiltonian as T plus V, the total energy. And if the Lagrangian doesn't depend on time, that total energy is conserved. But in general, H is defined through the Legendre transform, not through T plus E. T plus V, sorry. So this is not the definition of H. This is only true if the potential doesn't depend on the velocities. Okay? So this the Hamiltonian, in most practical cases now, is the total energy. And we just saw that what we've seen before, what we've learned before on the total energy being conserved, di L by di T equals 0, carries over to this Hamiltonian description. And it's particularly beautiful in the Hamiltonian description because di H by di T is equal to dH by dt. So if the Hamiltonian doesn't depend explicitly on time, then it's a constant. Any questions about that? Okay. So now let's do the canonical equations again, but from Hamilton's principle. So we just saw the canonical equations fall out from the transformations equations in the Legendre transform. So let's see how this fits into using Hamilton's principle. So let's look at the canonical equations from Hamilton's principle. So Hamilton's principle is the principle that underlies all of mechanics. Okay, so recall we had the action S to be the definite integral from some time t1 to t2 of this function L of qi dot, and t. And Hamilton's principle, let's call that HP, is that the equations of motion are derived from requiring that S be stationary. And so we saw that if L is indeed the Lagrangian, then the requirement that S be stationary leads to the Euler-Lagrange equations, and we saw that those were the correct equations of motion. They reduce, for example, to Newton's second law. Okay. So now let's see how we can derive the canonical equations. So remember, that's the equivalent of the Euler-Lagrange equations in the Hamiltonian formalism. It's the equations of motion from looking at the variation of this action. So we want to find when delta S equals 0. So let us consider delta S. So that's going to be delta of the integral t1 to t2 of L, qi dot, and t. So now we're going to use the definition of the Hamiltonian. So the definition of the Hamiltonian was the sum from I equals 1 to n of pi qi dot minus L. Appears that I forget the dt every time here. dt, dt. Okay. So that's using the definition of the Hamiltonian. Oops, sorry, that should be an H, not an L. Otherwise it doesn't make any sense. And H is a function of Qi, Pi, and T. Right? So the variation of the integral is the variation with respect to the Qi, right? So we got the equations of motions not by varying with respect to the Qi dots, but we varied only the Qi. Right, so delta Qi dot, if you do the variation of S when you have just the Lagrangian in it, if you look, you'll have a term with delta Qi dots in it. And the way we got rid of them was by using the properties of the delta. And so this is the same as delta of dQi by dt. And then the delta commutes with total derivative. So that's equal to d by dt of delta Qi. So that allowed us to write the delta Qi dots in terms of the delta Qi, since we're only considering variations of the Qi. So you can think of that if we're doing the sort of normal variational problem without worrying about mechanics, where you have this function L that depends on y prime, and x, right? You're trying to, say, minimize a path between 2 points. Then you only vary as the function y, not its derivative, right? And so that's the same thing here. When you do the variation of the action, it's only with respect to the variation of the coordinates, not of their velocities. Now, in the Hamiltonian formalism, so in the Lagrangian formalism, we have the coordinates and their time derivatives that we're kind of using as separate coordinates, but not really separate. Whereas in the Hamiltonian formalism, we treat the Qi and the Pi on an equal footing, so they're both coordinates. So in principle, they can both be varied, right? Now, the neat thing was that the whole point of the Legendre transform, we showed that the Lagrangian L doesn't depend on variations of the Pi. And the way we showed it was by showing that the Hamiltonian doesn't depend on the variation of the delta Qi dot. And that's how we said the Hamiltonian truly doesn't depend on the Qi dot, because the variation of the Hamiltonian doesn't have variations in the Qi dots in it. So, flipping that around, because the transform is completely symmetric, the variation of the Lagrangian is independent of the variation of the Pi. So you can vary the Pi and the Lagrangian won't change. Okay? So, from properties of the Legendre transform, varying the Pi does not change delta L, and thus the action is unaffected if the PI are varied independently from the QI. So we'll consider a variation now where we vary both PI and QI. And we know that varying the PI actually has no effect, but we'll be able to pick out terms that give us the canonical equations. So we'll pretend like varying the PI makes a difference, even though it doesn't. So the PIs will vary so that they go to PI plus delta PI, and the QIs will vary so that they go to QI plus delta QI. So if we calculate the variation of the action, we get delta S is equal to the integral from T1 to T2. Now the first term, so it's the sum of I equals 1 to N. So the first term up here, right, was PI QI dot, right? So I'm just rewriting this integral. So I'm going to take the variation, I'm going to bring the delta inside of the sum, and apply the product rule. So that gives us that first term, which is PI delta QI dot plus QI dot delta PI. All right, that's that first term. Now the second term, which was the minus H, so I'm going to write again H, I'm going to break up the variation of H. So that's going to be the sum from I equals 1 to N. And so H depends on PI QI. So that gives us di H by di QI delta QI plus di H by di PI delta PI. And this whole thing is integrated with respect to T. So here the variation of H, delta H, is the variation of H with respect to the QI and the PI. And remember, you don't take the variation with respect to the independent variable T. So there's no di H by di T term here. Okay, so you have to go back and look at the variational calculus section if any of these things confuse you as to what variables you vary and which ones you don't. Okay. So consider specifically this term here, the PI delta QI dot. So the PI delta QI dot, we just saw that we could write as PI d by dt of delta QI, right? And we can write that as d by dt of PI delta QI minus PI dot delta QI. All right, if I take the derivative of PI delta QI and apply the product rule, I get PI d by dt of delta QI, and then I get the second term, which is PI dot delta QI. So if I rearrange that, I can write the thing that's on the left as the total time derivative minus the thing that I don't want. But we already showed that the equations of motion are unaffected by the addition of a total time derivative to the action. In other words, this whole thing I have in brackets here, and the delta S, is really equal to the Lagrangian, right? And so what I've done is I've written the Lagrangian as this sum of all these things, and then using this last line here, one of those things is a total time derivative with respect of pi delta qi. So the equations of motions aren't affected by adding a total time derivative in the Lagrangian. So now when I rewrite this, I can actually write the underlying term here. I can just replace this by this term here, because the d by dt is not going to make any difference. So let me rewrite that, and what I'll do is I will write it all in one sum, right, because there's 2 times the sum of over I equals 1 to n. So delta S now I'm going to write as the integral from t1 to t2 of the sum I equals 1 to n. So that first term I'm going to write as minus pi dot delta qi. And everything else I'm going to write just the same. So qi delta pi minus di h by di qi delta qi minus di h by di pi delta pi. And so what I'm going to do now, I'm just going to group the terms that have delta qi's together and the terms that have delta pi's together. So that's equal to the integral t1 to t2 sum of I equals 1 to n. So let me take the terms with delta qi's in them. So I have minus pi dot minus di h by di qi. And that's the term in front of delta qi. And then I factor the term that has the delta pi's. So here I have qi dot minus di h by di pi delta qi. Now we require, from Hamilton's principle, right, delta S equals 0 for all delta qi and delta pi. All right, so the action is stationary, so this integral is stationary no matter what value of delta qi, sorry, the last term is a delta pi. Oops. The action is the variation of the action is 0 for all Qi and Pi. So all variations delta Qi and delta Pi. So for that to be true, no matter what choice of delta Qi and delta Pi I use, then the thing in parentheses must be 0. So hence, Qi dot must equal di h by di Pi, and Pi dot must equal minus di h over di Qi. And so again, these are the canonical equations. The next section in the notes is I'm going to skip. It's called symplectic notation. It's a way of writing out Hamilton's canonical equations in a vector form. It comes up sometimes. It's not super useful. It's well, it's not super useful. I mean, theoretically, to explore classical mechanics. It's useful if you're implementing a computer program that's solving many equations of motions at once. For example, you can think of calculating the path of a satellite through the solar system as it interacts with many planets. So that's, a lot of calculations, and so people have written specialized software to solve Hamiltonian's equation called symplectic integrators. And if you remember, Hamilton's equations, right, well, they're right here in front of us. The canonical equations are d by dt of something equals something else. And so you write the Qi's and the Pi's as one big vector, and the d by dt of that vector is equal to this other vector on the other side. And that allows you to integrate the equations effectively on a computer. So you can read through it. It's an easy read. It's only one page. But it's not terribly useful. It doesn't uncover any sort of theoretical prettiness. So let's just, so we'll skip section. How do you spell it? Symplectic. Okay. So what we'll do instead is we'll talk about phase space the phase space fluid and what's called Liouville's theorem. So I mentioned this before, but until now, when we were working with the Lagrangian, we were working in what's called configuration space. And when we work with the Hamiltonian, we work in what's called phase space. And in phase space, we consider the momenta as coordinates on the same footing as the position coordinates. Whereas in the Lagrangian, the velocities are just the time derivatives of the position coordinates, and they're not independent. So configuration space if you had, for example, a cannonball, so configuration space, the axes are the coordinates. All right, so if you're in three-dimensional space, there are three axes. So I'll pretend I'm in two-dimensional space. And if you have a cannonball, then it can start at one point in position in configuration space, and it can take different paths. Okay, so the shape of the path, it depends on the initial position, initial velocity, and of course the Lagrangian. Well, so maybe it's not the shape of the path, maybe it's just the path that depends on that. Now in phase space, that's not the case. So in phase space, now of course I can only do a one-dimensional problem, because in phase space, the momenta are treated as coordinates as well. So in phase space, we would write x as one axis and px as another axis. So it's a 2n-dimensional space if you have n-dimensional space, right? So now, if I have a particle that starts out in phase space at a certain position, it's going to take a path and end up at some later time at some other position. If I take a particle, so the shape of the path, or the path, is determined by the initial position at h, but it's not dependent on the initial velocities. So that means if I have a second point here, it's going to end up somewhere different. So given a certain Hamiltonian, the path of the system in phase space cannot intersect the path of a different system in phase space. So if you're at one point in phase space, the Hamiltonian will dictate where you end up later in time, and that path that you take through phase space cannot intersect any other paths. So if it did, that means that there's a point in phase space that could end up at two different points at a later time. So you can think of phase space so you can think of paths in phase space as the motion of a fluid. And an incompressible fluid. So given the Hamiltonian, right, that determines the shape of the flow lines. Now the phase space you can think of as a fluid where you have a bunch of points that can start at one point and end at a different point after a certain amount of time based on the shape of the Hamiltonian, and none of those paths cross. So it's like a non-turbulent fluid of different paths through this phase space. So we'll see an example of what one of these paths may look like. Okay? So let's do example 7.1 from the notes. So we'll do the simple harmonic oscillator. So the Lagrangian for the simple harmonic oscillator, L, is given by T minus V, so a half mx dot squared minus a half kx squared. Right? So step one is to calculate the Hamiltonian. So H is given by the sum of the Pi Qi dot minus L. So I equals 1 to n. So in this case, n equals 1, Q1 equals x, P1 equals Px. Okay. So we need to know what Px is equal to. So Px is defined to be di-L by di-X dot. So di-L by di-X dot is mx dot. So if I calculate the Hamiltonian, H, I get, so the sum from 1 to 1, so there's only one term, right? So I have mx dot, that's Px, times Qi dot, which is x dot, minus the Lagrangian, which is a half x dot squared minus, oops, so that'll be a plus a half kx squared. Okay, so then I have mx dot squared minus a half mx dot squared. So that leaves me with a half mx dot squared plus a half kx squared. And so you'll note that that's equal to T plus V, because the potential energy didn't depend on velocity. The total Lagrangian didn't depend explicitly on time. So that's equal to total energy, and it's equal to a constant. So we're not done. This is not the right way to write out the Hamiltonian, because remember the Hamiltonian is not supposed to depend on the Qi dots. Right, and here the Hamiltonian has an x dot in it. So we need to use this equation up here to find that x dot can be written as Px over m. So the Hamiltonian, which is a function of x, Px, and principal t, needs to be written as Px squared over 2m plus a half kx squared. So it should not have x dot in it. So that's our Hamiltonian. Alright, so the equations of motion are obtained from Hamilton's canonical equations. So Hamilton's canonical equations tell us that x dot is equal to di h by di p x. So if I do di by di px of the h that I have above there, I have a px squared over 2m. So if I take the derivative with respect to px, I end up with, oops, sorry about that. If I take the derivative of h with respect to px, I get simply p over m, px over m. And then the other canonical equation tells me that px dot is minus di h by di x. And so that's equal to minus kx. Okay? So that's the equations of motion. You can solve them independently for x and p, or you could substitute the equation for p into the one for x, or vice versa. So let's go back to the Hamiltonian and notice that the excuse me, the Hamiltonian is a constant, right? So since di h by di t equals 0, then dh by dt also equals to 0, and h is a constant. That means, so writing h as a constant, I have 1 over 2m px squared plus a half kx squared equals some constant, which I'll call E. We know that to be the total energy. So remember, P and X are variables that describe the system, and they should be treated on an equal footing. So we can draw where the system is in this so-called phase space. So let's draw the simple harmonic oscillator in phase space. So of course you all know in configuration space how the simple harmonic oscillator works, right? The configuration space is one-dimensional in X, and it goes back and forth between some minimum and maximum value of X, right? So in phase space, now there's two n dimensions, so we have to treat X and Px on equal footings. Now, this equation, Px squared, or something times Px squared plus something times x squared equals E, is the equation of an ellipse, right? So this equation defines an ellipse, which I'm going to try to draw. And so it's centered about 0. And if I have different values of E, then I have a different ellipse. So the maximum value that X can take is the square root of 2e over k. That's when p equals 0. And the maximum value that p can take is square root of 2me. So different ellipses, or different energies of the system, represent different ellipses in phase space. So back to this idea of the phase space fluid. So think of a simple harmonic oscillator with a certain amount of energy. So you can choose to put that simple harmonic oscillator with that given amount of energy in some position, at some displacement x and some momentum that corresponds to that energy. And so that'll be a 1 point on one of the ellipses that's determined by the energy. And if you let the simple harmonic oscillator progress through time, it's going to move around that ellipse until it comes back to where it started. So this particular Hamiltonian in phase space gives motion that are closed and in the shape of an ellipse. And if you have a different simple harmonic oscillator with the same oscillator but a different energy, it's going to move around in phase space on a different ellipse, and it's never going to intersect the other ellipse. And so you can think of this phase space with the Hamiltonian as a bunch of different paths that the system takes, and it behaves exactly like a fluid, an incompressible fluid. You can't have two paths intersect each other, because that would mean that a single initial condition with equations of motion could lead to two different possible paths in the future, or positions in the future. All right, so the fact that classical mechanics is deterministic means that no two paths can intersect. So it behaves exactly like an incompressible fluid. So let's finish up by seeing how exactly it behaves like an incompressible fluid. So remember now, we're talking about this phase space, and the system can move through phase space. Right? So it has velocity in phase space, and the components of the velocity in phase space are x dot and px dot. Right? So x and p are like coordinates of this new space, and so the velocity in that new space is the time derivatives of those two coordinates. Okay? So consider the continuity equation from fluid dynamics. So from fluid dynamics, we have di rho by di t plus the divergence of rho v equals to 0. So rho is the density of the fluid, and v is the velocity field of the fluid. So this equation, the continuity equation, tells us that if you have some fluid flowing into a particular volume, it has to flow back out. So it means that there can't be any liquid that disappears or reappears in a small volume for a continuous fluid, unless you have a source. And if you have a source of fluid, like the end of a hose, then the right-hand side of the equation wouldn't be 0. Now, in particular, for an incompressible fluid, we have the density of the fluid doesn't change with time. So di rho by di t equals 0. Okay? So that means that if that's the case for an incompressible fluid, then the divergence of the velocity field, which is a vector, so right, is equal to 0. Right, because rho is just the function, so it comes out of divergence. Okay, so that's from fluid dynamics. So let's see how that could possibly work in our phase space. So if we consider a physical system in phase space as a fluid. Okay? So then the velocity vector in phase space, let me write it as all of the time derivatives of the space coordinates, and then all the time derivatives of the momenta coordinates. Right? So in that space that I've labeled as 2 n-dimensional space with, n coordinates and n momenta, then the velocity through that space is the time derivatives of all those coordinates. However, we know from the canonical equations that Q1 dot is di H by di P1. And P1 dot is minus di H by di Q1 right, that's just from the canonical equations. So let's apply the continuity equation. So let's apply the continuity equation of fluid dynamics to our phase space fluid. So I want to write that the divergence of the velocity field is equal to 0. So what that means is I go the sum from I equals 1 to n. So remember the divergence, this means in Cartesian coordinates that di Vx by di x plus di Vy plus di y plus di Vz by di z equals 0, right? It's the scalar product of the Nabla operator with v. So if I do that to our velocity vector, right, I have di Vi by di Qi. So that's the first group, right? There's 2 groups of terms in our velocity vector from the phase space. There's the Qi dots and the Pi dots, right? So I'm just going to write them as one. So there's 2 n coordinates in our velocity fluid vector, right? So the sum should go from I equals 1 to 2n. So I'm just going to write it as a sum from I equals 1 to n, and then the other terms are going to be, so it's di vi by di qi, that's the first n terms, and then the next n terms are di vi plus n plus I divided by di pi. Does that make sense? Or let me know if that doesn't make sense. Because this divergence should have two n terms, and indeed it has two n terms, but I can write it as a sum from 1 to n. That way I can, the indices on the q's and p's only go from 1 to n. Okay, so that's equal to the sum from I equals 1 to n. So now the vi, right, are just the qi for the first n term, so that's di qi dot by di qi, and then the second term is di pi dot by di pi. Now let me insert the canonical equations. So here I have the qi dot, so that's di by di qi of qi dot, which I can write as di h by di pi. Similarly, I have di by di pi of pi dot, so I have di by di pi, and the pi dot I can write as minus di h by di qi. So that's equal to 0 because the partial derivatives commute, right? Di by di qi and then doing di by di pi is the same as doing di by di pi and then di by di qi. And so indeed, the divergence is equal to 0 for the phase space fluid. So that's Liouville's theorem, is that the system behaves like an incompressible fluid in phase space. So that's kind of neat. Alright, so that's a good stopping point. Any questions about this? It was pretty technical. Yeah, question from Michelle? Oh, okay, fine. And so just in case you missed the first part of the notes of the course, of the class, I re-uploaded the notes because they were missing a section and they had some small mistakes in them. So for chapter 7, I've re-uploaded them. You should re-download them. Apologize if you already printed them. Okay, well that's it for today then. Thanks everyone.